So liquid nitrogen, you can do some amazing things with it. And usually the students hate this. They would rather take this home to their mom. But this is science. So I'm going to see what happens when we freeze a rose in liquid nitrogen. First, you might see it start to boil. And as it boils, any liquid in it is going to be frozen and it'll stop boiling, and the properties are completely changed. Looks pretty cold to me. Boiling's almost stopped. I wonder if it still has the same properties. One way to find out. Here we go. Looks the same until I do this. That's pretty cool. If it works with one, how about 9? So I got 9 of them. We'll put all them in here, all 9 of them. And what you see right here is 9 frozen flowers. Day 9, cryogenics, things that are cold. And one of the coldest things I know is liquid nitrogen. Now liquid nitrogen is everywhere. In fact, it's 70% of our atmosphere. But there was a couple scientists that found a way to liquefy it. And this is liquid nitrogen, and it is very, very cold. Minus 320 degrees below zero. But more importantly, it expands. It expands 694 times the ratio of its volume. So it's so cold that if I put my hand in it, that would do a lot of damage. But there's a thing called the Leidenfrost effect. So when I pour this actually onto the table, this table is so much hotter than this liquid nitrogen that it will boil and make a vapor barrier, and you won't even see it get the table too cold. Or even on the floor, if I try it right down here on the floor. Here we go. That's pretty cool. But if you really want to see it, let's pour some in a column here. And you notice that hot goes up, cold goes down. And all these vapors, this is water vapor from my breath, that's going down. That's not nitrogen, because nitrogen is odorless, colorless, and basically inert. You can't catch it on fire, you can't do any of that. But if I add a little bit of water to it, that will definitely cause it to start to change its properties. That's kind of cool. Not the nitrogen, but the water. And there's a lot of cool things you can do with it. Let's see some more. So, I have here a piece of rubber tubing, and matter has different properties under different temperatures. So when I drop this down in this liquid nitrogen, first thing it's going to do, you can start to see some of it come out the top there. But I am now super freezing this rubber. And I wonder if it's going to have the same properties it had at room temperature. I kind of doubt it. This part up here, still bendable. This part down here, not so bendable. In fact, it's lost all of its properties of rubber, just like that. And it bounced in there.
I want to do a fun experiment with you where I'm putting liquid nitrogen inside this Pringles can that is empty because Mr. Crosslin ate them all. So as we know, liquid nitrogen right now is boiling because it's above negative 320 degrees. And it's turning into a gas. So as we know, gas takes up space, it expands as it heats up, builds up more kinetic energy. Seal this up and pressurize it, and it pops the lid off. Pretty cool.
Justin did a really good job with the Pringles, so I'm going to try a metal can. That might take a little more force. Let's see what happens. Liquid nitrogen expands 694 times its volume, and hey, that was a good one. Maybe one more. Ready?
we've been talking about expanding gases. So now I want to dip a balloon that's been blown up into liquid nitrogen. And we can see that the air isn't going to expand. This is actually going to contract because the cold nitrogen is slowing the air molecules down into the balloon, and it's losing kinetic energy, and we can see it's shrinking and shrinking. And eventually, if you kept holding this down, it would get crinkled up because it's also rubber, the balloon, and it gets hard and crispy. And you can hear it. And what's really cool is when we take it out, it's out of the cold. It's warmer air. So it's speeding up the air molecules, and they're bouncing off each other now. And as they're bouncing off, it's expanding slowly. And eventually, it's going to expand right back to the original volume and shape that it was from the beginning. Pretty cool stuff.
Another way we can use cryogens is to cool superconductors. And I brought with me my superconductor trap and a couple of discs here that are made of yttrium, copper, barium oxide, ceramic. And when you get these discs really cold, amazing things happen. Before I start, I want you to notice that these discs are non-ferromagnetic. They're not attracted to each other. They're not attracted to the track. Notice that they don't repel each other either. But when we cool them down to negative 320 degrees Fahrenheit, the crystal lattice of an yttrium barium copper oxide starts to open up what are called flux tubules, little openings in the crystalline lattice that are imperfect, that allow for magnetic vortices to swirl through them and to hold them in place. Check out what happens when I now take a cooled superconductor and put it over a magnet. It starts to levitate, and I can even push it along the track. Now I'm pushing it with a plastic tong because I don't want the metal tong to stick to the magnetic track, but also because I don't want to touch it with my hand because that'll warm it up. And when it warms up, it loses its superconductivity. This track was made by Dr. Boris Almog of the University of Tel Aviv. He's studying the Meissner effect, quantum locking, and flux spinning. So when I told you about those microtubules that allow for little magnetic vortices to pass through them, that's his research that is affecting how well these float over the track. Here's a larger one. Notice when it passes over the other superconductor, it's not attracted to it. It just simply floats right over it. Quantum levitation, brought to you by Science Claus.
Here's another cool science experiment with liquid nitrogen, where if you pour it slowly enough on top of warm water, and I colored this water so you could visually see it since it's clear, you can see the liquid nitrogen floating across the top because it's less dense than water. Now, you might be wondering, why is it moving? Well, with my hand tilting the cup and it hitting the water, obviously I'm transferring some of my energy and gravity's pulling it. But you can even see, if you look close, ice from the water. That liquid nitrogen is freezing some of that water and creating an insulator where it's separating the cold from the heat. It looks really cool. It almost looks like Ghost on water. So we've been dealing with liquid nitrogen, a really cold product. So now I'm going to do a cool experiment with dry ice. Now dry ice is extremely cold. It's carbon dioxide frozen into a solid at negative 110 degrees. Now, when we put it into water, it speeds up that process. Now, something interesting about dry ice is, so dry ice, as it changes states of matter, it goes from a solid straight to a gas. It skips the liquid phase, which is called sublimation. So as you're seeing right now, this is in water. Inside this container here, I have a tube, and I'm gonna build up the pressure a little bit, and as you're gonna see, it's gonna start coming out the ends. But what's really cool, when you can put this into soap mixture, you can make these awesome carbon dioxide filled bubbles. As you dip it in, you actually can even sometimes hold some of them depending on the gloves that you have. And as you can see, they're bouncing. Look at that as I poke it. Oh, it's bouncing around. It's awesome. Hot air balloons go up, cold air balloons go down.